Hi, Assalamualaikum. We will be presenting our case study about ground subsidence in Bangkok. These are our group members.
Ground subsidence is a major urban geotechnical issue that occurs when the ground surface gradually sinks due to changes in underground soil conditions. In Bangkok, this problem has become increasingly serious because of excessive groundwater extraction, rapid urban development, and the presence of soft clay soil. Continuous pumping of groundwater reduces pore water pressure, causing soil particles to compress and resulting in land settlement. As Bangkok is a low-lying and highly populated city, ground subsidence increase the risk of flooding, infrastructure damage, drainage failure, and public safety hazards. Therefore, sustainable engineering solutions and effective regulations are essential to minimize future settlement, improve urban resilience, and support long-term sustainable development.
On this slide, I will explain the main causes of land subsidence in Bangkok. Land subsidence happens due to the interaction between groundwater extraction, soft soil condition, and rapid urban development. The first factor is excessive groundwater extraction. When groundwater is pumped continuously, the pore water pressure inside the soil decreases. As a result, the soil particles move closer together and soil compression occurs. The second factor is Bangkok's soft clay and silt layers. These soils are highly compressible and undergo long-term consolidation settlement when subjected to pressure changes. The third factor is urban development. The construction of heavy buildings and infrastructure increases vertical loading on the ground, which accelerates settlement in the soft soil layer. When these three factors combine together, the ground surface gradually sink over time, leading to land subsidence problem in Bangkok. This slide shows the mechanism of soil consolidation settlement. Before groundwater extraction, the groundwater level and pore water pressure remain stable. After excessive groundwater extraction, the groundwater level drops and pore water pressure decreases. This process can be explained using the effective stress equation. In geotechnical engineering, effective stress is equal to total stress minus pore water pressure. When pore water pressure decreases, the effective stress increases. As a result, soil particles move closer together, causing consolidation settlement and ground subsidence. This may lead to infrastructure damage such as cracked roads and building settlement. This slide explains the hydrological interaction and drainage failure associated with land subsidence. Under normal conditions, water flows efficiently through drainage canals and is discharged properly. However, during heavy rainfall, the drainage capacity may be exceeded. Water flow becomes slower and floodwater remains for a longer period. Bangkok is particularly vulnerable because it is a low-lying basin area that experiences heavy monsoon rainfall. In addition, urban drainage congestion and sedimentation reduce the efficiency of the drainage system. Land subsidence worsens this condition because the lower ground elevation reduces the effectiveness of gravity drainage. As a result, flooding risks increase, and this can affect public safety, sanitation conditions, and urban infrastructure. This slide summarizes the complex interaction between engineering factors and their impacts. Several engineering factors contribute to land subsidence, including soft soil settlement, groundwater extraction, urban flooding, drainage failure, and urban development loading. These engineering problems create significant societal and environmental impact such as unsafe housing condition, road and infrastructure damage, economic losses, poor sanitation, environmental pollution, and disruption to community activities. From the safety and regulatory perspective, civil engineers play an important role in ensuring public safety, implementing groundwater regulation, improving drainage management policies, and promoting sustainable urban planning. Therefore, land subsidence in Bangkok requires an integrated and sustainable engineering approach involving cooperation between engineers, authorities, and stakeholders.
In the case of ground subsidence in Bangkok,
Civil engineers play an important role in protecting public safety and ensuring infrastructure stability. Engineers are responsible for conducting proper geotechnical investigations because Bangkok is built on soft clay soil that is highly susceptible to settlement and subsidence. Civil engineers must also ensure that buildings, roads, drainage systems, and foundations are designed safely according to engineering standards and regulations. From an ethical perspective, engineers must prioritize public welfare by reporting risks honestly and preventing unsafe construction practices. In addition, engineers should promote sustainable engineering solutions such as groundwater control, soil improvement, and flood mitigation systems to reduce long-term environmental and societal impacts. Ground subsidence in Bangkok involves multiple stakeholders with different priorities and concerns. Government authorities are responsible for enforcing regulations and ensuring public safety. Civil engineers provide technical analysis and safe infrastructure design. Developers and contractors focus on urban growth and project completion, while residents are concerned about flooding, property damage, and infrastructure safety. Environmental organizations are also important stakeholders because excessive groundwater extraction contributes significantly to land subsidence in Bangkok. Therefore, engineers must balance economic development, environmental sustainability, and public safety when making engineering decisions. This demonstrates the importance of stakeholder integration in solving complex engineering problems. To reduce ground subsidence problems, Bangkok implemented several regulations and engineering control measures. One important measure is groundwater extraction control because excessive groundwater pumping is one of the main causes of subsidence in Bangkok. The government also introduced land monitoring systems and stricter geotechnical investigation requirements before construction projects can proceed. In high-risk zones, construction activities are more closely monitored to reduce settlement risk and infrastructure damage. These regulations are important because they help reduce future subsidence, improve flood management, and protect public safety. For civil engineers, compliance with regulations and engineering standards is essential to ensure sustainable urban development and prevent engineering failures.
Sustainable engineering solutions are built upon four fundamental pillars: groundwater extraction control and artificial aquifer recharge, deep soil improvement and ground stabilization, sustainable urban planning and load management, and smart monitoring with satellite and IoT sensors. Groundwater extraction control and artificial aquifer recharge are important engineering solutions used to reduce ground subsidence in Bangkok. Excessive groundwater pumping lowers underground water pressure, causing soft soil to compress and the ground to sink. To solve this issue, authorities can control groundwater usage and replenish underground water naturally or artificially. This solution also uses advanced technologies such as satellite deformation mapping, IoT ground movement sensors, real-time warning system, and predictive AI modeling. These technologies help engineers monitor land subsidence in real time, allowing early detection of dangerous settlement and faster engineering response. It also supports SDG 12 by promoting efficient and sustainable resource management. From the societal and safety perspective, controlling groundwater extraction helps ensure long-term clean water supply, reduce flood impacts on communities, and improve public quality of life. It also reduces building settlement rates, prevent road and utility damage, and improve infrastructure stability. From the regulatory and environmental perspective, these solutions require strict groundwater extraction laws, continuous environmental monitoring, and compliance with water management regulations. Environmentally, it helps prevent groundwater depletion, protects underground water balance, and reduce environmental degradation, supporting sustainable urban development in the future.
The second pillar focuses on geotechnical engineering methods designed to strengthen weak soft clay soils and increase load-bearing capacity. Primary engineering solutions involve deep cement mixing (DCM), jet grouting, vibrocompaction, prefabricated vertical drains (PVD), and controlled preloading. These methods help reduce future settlement, improve soil stiffness, and safely support building transport infrastructure. In alignment with SDG 12, these practices promote durable infrastructure and the efficient use of construction materials, thereby reducing future repair and reconstruction needs. Implementation requires balancing several factors: societal, improving the reliability of public infrastructure and reducing economic losses from repairs to support safer urban development; safety, minimizing road and building settlement while reducing foundation failure risk to improve structural stability; environmental, acknowledging that cement usage may increase carbon emissions and that construction activities may generate waste, thus requiring sustainable material management; regulatory, following strict geotechnical design standards, conducting environmental impact assessment (EIA), and complying with construction safety regulation. Thirdly, a city planning strategy is employed to control land use, building density, and infrastructure placement to minimize stress on vulnerable ground. Key engineering solutions include limiting high-rise construction in critical zone, utilizing subsidence zoning maps, implementing smart building codes, developing green infrastructure, and promoting distributed urban development. These actions reduce excessive surface loading and prevent concentrated settlement to support resilient city growth. This strategy supports SDG 12 by encouraging responsible urban development and efficient land resource use. Relevant considerations include societal, promoting balanced city development and improving long-term living conditions while reducing disruption to communities; safety, reducing flood and settlement risk and preventing overdevelopment in vulnerable areas; environmental, encouraging sustainable land use and supporting green infrastructure to improve urban drainage system; regulatory, requiring strict zoning enforcement and effective land use planning policies in compliance with building codes. The final pillar emphasizes smart monitoring with satellite and IoT sensor to track land subsidence in real time. Solutions such as satellite deformation mapping, real-time warning system, and predictive AI modeling ensure early detection of dangerous settlement and support fast engineering intervention. This continues the advancement of SDG 12 through data-driven infrastructure management. This monitoring is vital for the expansion of the pipe water supply system. Considerations for this expansion include societal, protecting communities through early warning systems, reducing economic damage, and improving public awareness; safety, detecting dangerous ground movement early to prevent major structural failures and support fast engineering response; environmental, improving maintenance efficiency and reducing unnecessary reconstruction waste to support sustainable infrastructure management; regulatory, establishing government monitoring policies, fostering data sharing coordination between agencies and complying with infrastructure monitoring standards.
In conclusion, ground subsidence in Bangkok is a serious geotechnical and environmental issue caused by excessive groundwater extraction, soft soil conditions, and rapid urban development. If not properly controlled, it can result in flooding, infrastructure damage, environmental degradation, and risk to public safety. Therefore, sustainable engineering solutions are very important. Groundwater extraction control, deep soil improvement, sustainable urban planning, and smart monitoring technologies can help reduce settlement and improve long-term urban resilience. These engineering approaches also support SDG 12 by promoting responsible resource use and sustainable infrastructure management. Thank you.